Hey, hello, everyone. Today, I have to use a different format to teach this lecture because I'm sick today and I got influenza B. I don't want to get anyone infected if I am teaching this lecture in the classroom. What I'm going to do is I'm going to record a video for this lecture, lecture 10. Then I will upload it to YouTube, and I will send the linkage by Canvas announcement and also by email. Make sure you get it, okay? And I apologize for the late notice, and yeah, it's getting very severe today. So yeah, I don't want to get you guys impacted. Okay, let's get started. And we're going to talk about group 16, 17, and 18 today. And here is a periodical table, and here we highlight the group 16 here. So we have oxygen, sulfur, and selenium, and tellurium, and polonium. Okay, the reason we call it group 16 because at outer orbit, this group has 6 electrons, right? Then for oxygen, so then we can write the electronic structure with core as helium, and we have 2s 2 and 2p4, right? That's what we have. So make sure you can write the electronic configuration for other element. Okay. And by the way, and for this one, so the element tellurium. So there's a city called T telluride, UAD. That's in Colorado. So this city actually get named from this element because the city produce tellurium-based minerals, so that's why they get named there. Okay, that's just a side story to share. Okay, and here basic chemical physical properties of group 16, and let's look at the interactivity. So that's the most important property for element. You can see oxygen has 3.4, and when you go to polonium, that's only 2.0. So you go, that's a trend, okay? You increase from right to from top, from increase from bottom to top, but unslide right to left, okay? Anyway. So as you recall, for the entire periodic table, in the same period for main group, right? For main group elements, in same period, if you move from left side to the right side, you increase electron activity. Okay, yeah, make sure you can remember the trend. And if you look at the covalent radii, so you can see that's increased in this way. That's the increase, okay? Because when you have higher electron activity, they tend to hold electron tighter than elements with smaller electron activity. And also we have same trend for the ionization energy, okay? Ionization energy, but we have exception for the electron affinity because this one, we have highest one for sulfur. But it's not, we don't have trend here, okay? Okay, let's put a star sign here. Okay. And you can see oxygen is a gas, and the other one are solid. Okay, that's a gas at room temperature. So all other is are solid, okay? And group 16, they tend to form binary compound with hydrogen, halogen, and oxygen, and also metals. There's so many metal oxide almost all metal form metal oxide, metal sulfide. Yeah, especially metal oxide. Okay, very, very common. Then for the these slides, we're going to use example of hydrogen binary compound. We have water, hydrogen sulfide, hydrogen selenium, hydrogen tellurium, hydrogen polonium. Okay, and if you look at those compound, okay, and you can see the melting point, and this one, the water has highest melting point, and that's a trend. You increase from right to left. Okay. Oh, not increase, because I need to course this out. Sorry. That's not the increase. We don't get a parent trend. Okay. Anyway, so water has highest melting point and boiling point, but we don't get this apparent trend. Okay, apparent trend here is lower, higher. Okay, lower, higher. We don't get trend. Okay, we don't get trend. Okay, always you get exceptions. Okay, and abundance is, you can see the abundance consistent with the interactivity. So oxygen, hydrogen, they form shorter bond compared to other ones. So you see smaller. But the bond strengths, okay, if we add another item here, bond strengths, ENGTH, that's going to be this strength. Okay, that's going to offset to the bondingness. Okay, so another point we need to emphasize is acidity, constant acidity. That's pKa. Remember, you can right now how to calculate the pKa. You should remember the equation for pKa, right? So make sure you can do that. Okay, then here you can say which one has a higher pKa. Water, right? That's a trend. Say because hydrogen bond is strong, hydroxide bond is stronger than other one, so it's hard to release a proton from water compared to other ones. So that's why I can say, if I ask a question, which one, if I give this 4 compound, I ask which one is strongest acid, then you will say this one. Okay, this one. Okay, make sure you remember the trend for this one. Okay. All right. Then let's talk about the common compound, representative compound for group 16. And group 16, besides binary compound, they form, ring type and chain type, and cluster compound. Okay, anionic and cationic, and also they formed neutral heteroatomic ring compound. Okay. So then let's look at these examples. The first one is tetraphthalate ion. That's a dianion. Okay. Then, and make sure you know the oxidation state number for each sulfur. Okay, Okay. And always we have oxygen as -2. Pretty common. That's the most common oxidation state for oxygen. Okay. Then you are going to have the sulfur here is what, and we need to assign this one as S1. So that's S2. We have 2 S1, 2 S2 here, right? This terminal with 3 oxygen and internal sulfur is bound with sulfur. Okay. And in this case, and we can calculate the oxidation states for this one. Okay. And we have 3 minus, and we can put this one as +6 and S2 as 0. So when element connect with same element, so we treat as 0 valence. Okay. And this one, similar structure as we have penta 5 sulfur, but we have 3 internal sulfur as dianion. So this one is S3 2 minus. So that was typically produced from S8. S8 is a ring compound. Okay, that's just that's a 8 sulfur ring type compound. So when you reduce that, you get to there. But here we get S0, but here it's S minus 1 and S minus 1 here. Okay, so that's oxidation state. This one is a selenium cluster, 11 selenium. And here is 7 tellurium, okay? And here, and last two are heteroatomic cluster. So this one S4 and 4 and S2 and 2, because nitrogen has larger electronegativity than sulfur. So we will treat this one as negative charge. This one is going to be here, the positive, okay, the positive charge for sulfur, okay, positive charge, negative charge for nitrogen, okay. So in this one, we can code this as +2 and -2, okay. All right, let's move to group 17, okay. So we have group 17, fluoride, chloride, bromide, iodine, and astatine. Okay, the reason we call this group as 17 because they adopt, two, NS to NP5. So outside they have 7 electrons, okay? And make sure you can write electronic structure for this group, okay? And what's a group oxidation number? And GROUP group oxidation number. So what's that? That's highest oxidation number. That's +7. Okay, that's easy to memorize. Okay, just that's corresponding to the electron in the outer orbital. Okay. Then here is a table to show the basic physical chemical properties of this group. Okay. We can have, let's look at it also. The first one for the electronegativity. So you can see fluoride 4, and we decrease when we from top to bottom. Okay, on slides we can see from right to the left, we see increase trend. So that's a trend consistent with the periodic table. Okay, and also consistent with the electronegativity, we have the trend for the covalent radii. Okay, so that's increase. Okay, we have larger electronegativity tends to form shorter covalent radii. Okay, and you see then we have melting point. Okay, melting point, and you can say that's a F2, that's a gas. Okay, chlorine, that's a gas. Then bromine is a liquid. Okay, iodine, you can see melting point, it's become a solid. Okay, then in this case, the first ionization energy is also consistent with the electron activity. Okay, they are consistent. Okay, in this case, in group 17.